Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2, with the course code PHY 222, we are at the lecture number 13, and the topic is some special second order linear equations. In my previous lectures, I have explained the second order linear equations with the right hand side equal to 0 and also not equal to 0. Those equations are very important in many physical problems, and we need them to model in physics electrical and mechanical phenomena. But we can have some second order linear differential equations where not only the right hand side is not equal to 0, or we have the coefficients that are not constant. Because previously studied equations, we always had constant coefficients, but now we want to look at some special equations where coefficients are not constant, and we will try to see that how we can solve these equations. So how many types of these equations actually exist? So the answer is that there are many types, but in today's lecture I will be talking about only few of them. The first one is the case when equations, the second order linear differential equations, are with missing y, or independent variable is missing. So we will talk in detail about such equations and the method of solving them. Second type of equations where the constant coefficients are not constants are equations with x being missing there. So in first one we have a one variable missing, and in the second one we have the second variable missing, and in the third type is of this type. As you can see that we have double derivative, but the single derivative is missing. So you can see that these are all possible situations we are considering. In first one we have y missing, in the second one we have x missing, and in the third one we have the first derivative missing, although we have some function of y there, but we have the second derivative, first derivative missing here. In the fourth in the fourth case we will consider the Euler-Cauchy equations, and we will see that how we can solve such equations and which kind of physical phenomena they can model. And in the last we will see another type of equations where we can reduce the order of an equation. For example, we can reduce it from the second order to the first order linear equation, and then their solution are quite easy. So there are also other types of equations. This is not the exhaustive list of all sorts of equations, but these are the most common equations. In coming lectures we will also deal with other methods and other equations which are not included here, but these are a few equations which are important, and therefore it is essential to know the methods of their solution. So let's start with the first case. In first case, as I have mentioned, that these are the equations where we have y variable missing. So what we shall do when y variable is missing? In such situations we make substitutions. So we make some kind of substitution, and from this substitution we get the equation into a simple form and then solve it. So for example, we can put the first derivative of y equal to another variable, let's say call it p, and then the double derivative of this y is equal to p prime. So if we make this sort of substitution into an equation where y is missing, you see there is no y, we have y prime and we have y double prime, but if we make this substitution, that putting y prime equal to p and y double prime equal to p prime, then we can solve that equation easily. So then how we solve it? The method is that after these substitutions, the resulting equation becomes linear in p. So you will see that in such equations, although y was not there, but we made a substitution, y prime is equal to p and y double prime p prime, and we will see in examples that after these substitutions, equation is linear in p, and once we have a linear equation, what we do is to solve it for p. So because it's a linear equation and we already know that how to solve linear equation in some variable, here that variable is p, so we solve it as a function of x, and after the solution, when we get back the solution and we put back p is equal to y prime, because we know our substitution, that was y prime is equal to p, and when we put it back, what we get is the first order linear equation. So then we solve this because we still have first derivative involved. Remember, it's not p is equal to y. Otherwise, if we have p is equal to y, there's no point of making substitution, but we have p is equal to y prime. So once we have y prime and we know the p, but still we have to make another integration or some method of solution in the first order linear equation. So we solve it for the first order linear equation in y, and in this way we have the final solution. Okay, so this was the first case where y was missing, and the method is very simple and straightforward. We make substitution of y prime and y double prime and get the equation in terms of a new variable, let's say called p, and then it is a linear first order differential equation. We solve it for p, and then we put back the p in as a y prime, but it's again a linear first order differential equation. We solve it again for y and get the final solution. Okay, so far so good. Now we move towards our second case, and the solution of the case b, where we have equations with x missing. And when we have x missing, so again we will go for the method of making a substitution. So either y is missing or x is missing. In both cases we will make a substitution. In this case, again we will make y prime is equal to p and y double prime is equal to dp by dx. But since x is missing, so how can we differentiate p with respect to x? So that's the problem. But since we know that, we can use the chain rule. In chain rule, we know that p is a function of y, because y is there since x is missing. So if we differentiate p with respect to y, and since y is a function of x, after all the whole equation is a function of x, so using this chain rule and putting dp by dy is equal to p from the first substitution, we get p is equal to dp by dy. So in this case, also making such a substitutions, what we get is the first order linear equation, and in this first order linear equation, then we can solve it by integration and then putting back the substitution and then solve it again and get the final solution. So this was the method for the solving case b. In order to get all this explicit, I will give you now an example where you can see this happening. So let's take an equation, and in the case b, case a is very similar to it, even simpler than the case b. So let's talk about this equation. That's an important equation. For example, you can think of it that a particle of mass m is moving in some potential, let's say in a spring potential, where you have this ky as a restoring force, and this as a damping force for any L greater than 0. So we have the particle of mass m, and we have this damping force, and we have this restoring force. So you might think this problem as a simple pendulum or mass attached to the spring, where a particle attached to the spring or a pendulum are making forced vibrations under certain force. And if you look at this equation, then it is equation with x being missing, because if you look at over here, or t being missing here, the role of the x is being played by the variable t. So you see that here we have the second order differential equation. So y is here as well. T, we are differentiating with respect to t because y is a function of time, time or t are any variable, but t is not appearing in any term. For example, t is not appearing here, t is not appearing here, t is not appearing, so t is missing. So t is actually a independent variable which is missing. In the previous case we had a dependent variable which is missing, but here we have an independent variable which is missing. So this equation we can now solve by the method of substitution, but before that I would like to put it into a more simpler form, like this one, by having some assumptions. For example, if you put m is equal to 1, y is equal to 1, and t is equal to 0, so if you use these conditions these initial conditions, then our equation is a little bit more simpler, and we have d square y dt square plus 2 dy by dx y is equal to 0. And now this equation is, although it's just the same equation, but it is more simpler to solve. And if we solve this equation, we will go towards the method of substitution, as we have already learned that dy by dt we can put it equal to p. Remember now that the role of the x is being played by now t. So if I put dy by dt is equal to p, then d square y by dt square is equal to p dp by dy. You can do this calculation for yourself, that there is a chain rule used, because I have put dy by dp by dy over here is equal to p, and then the dp by dy is here. So so this is the second derivative and this is the first derivative, and then this equation which we already know is transformed into this form. Now you can see it is an equation in p, and p is appearing now here, and this is an equation in p and y. And now we can solve it, okay, first of all put it into a simple form by taking this 4p to the other side and y all to the other side. This is a very simple steps. You can see, taking it y to the other side and then dividing by 4p, we get this equation. And this is a sort of remember, this is a Bernoulli equation. We have already done that, such types of equation where p and q, you can recognize what is p and what is q, and now we can we already know how to solve the Bernoulli equations. So so you have seen that in this case we have reduced the equation to the linear first order or sort of Bernoulli equation, which are easier to solve. So we can now solve it for the case we have n is equal to -1. So we put p square is equal to z, as we have learned for the Bernoulli equation. So dz by dy will be equal to 2p dp by dy, and this substitution will give us the equation into this form. If you put the substitution into the equation we got in terms of p, yet another substitution, and we transform the equation into variable z and y. And then the solution is, if you remember from Bernoulli equation, that this is the solution, and just put that into integral and calculate that integral, and you will get this value easily. And after that the z is determined by taking this into the other side, and since we know that we can have a negative acceleration at in the beginning, so we will have the positive sign over here for the restoring force to work, because we will have to be careful with these signs to put the restoring force, the sign of the restoring force correctly. So this is what we get at the end, z. And finally, the value of c can be determined from initial conditions, because there is a constant of integration involved that can be determined from initial conditions. For example, these are the initial conditions, that y is equal to 0 at t is y is equal to 1 at t is equal to 0, dy by dt is equal to 0. And if we put these conditions into the equation, what we get that the value of c is equal to minus e raised to power minus 1. So if you put the value of integration constant into the equation, this is the form that equation takes, and this is the final solution we have got. So you have seen generally that in first and second case, when x and y are missing, we make substitutions, and these substitutions bring the equation into linear first order differential equation, and then we can solve it easily. Okay, so let's now move towards the third case and see how we can get the solution in the case C. And the case C, remember, was this equation, that is y double prime f of y is equal to 0, where the first order first derivative is missing. So to solve this, what we do is to bring in the y prime, that is the first derivative. So we multiply y double prime plus fy is equal to 0 with y prime. As you can see here, y prime y double prime fy is equal to 0, or we can write it as y prime dy prime, or fy dy is equal to 0. So after putting into this thing, we get the general solution of this equation equal to 1 over 2 y prime into fy by integrating, and by integrating for the one thing, and by integrating once, and we get this form. So it is good to consider an example of the case C. Here you can see that this is the Newton's second law, and this is a second order linear differential equation, md square x by dt square and f of x. And in this case, you see this is a very famous example that the first derivative is missing, that is d by dt x is not here. So, and if we want to solve this equation, how we can do this? And you can recognize or you can identify this equation with this, because y double prime is over here, this one, and this is some constant, some function of x. So this is this sort of equation. If you bring it over here, then this will be equal to 0. And for this, if we multiply this equation by v, that is velocity dx by dt, and integrated with respect to t, we get mv dv by dt of x dx by dt, or mv dv is equal to this thing. And after the integration, we get half kinetic energy, half mv square f of x dx is equal to constant. And then this is the final solution which we got. So you have seen in the third case that if the first derivative is missing, then what we do is simply multiply the equation with this, with first derivative, and then integration gives us the final solution. So now we move towards our fourth case, which is the Euler-Cauchy equation. That is our fourth case, and this is this sort of equation. So you see now this is second order linear differential equation, but the coefficients are now multiplied with the x square x, and now the coefficients are not constant. They are not constant. Otherwise, it would have been simple to solve the second order linear differential equation with constant coefficients and right hand not equal to 0. But in this case, we get these extra x multiplied with the constants. So how do we solve such equations? For here, what we do is that we put x is equal to e raised to power z, and then x, if we differentiate x, dy by dx then equal to dy by dz, and this equation turns out to be x square d square y dx square is equal to d square y dz square minus dy by dz. And then Substitution of this gives us these equations, put the equations into this form. So what we have done by these substitutions, I shown you on the last slide, that we have removed x square and x from the first and second term and brought it to the right hand side and put it as a function of this exponential. So then you know that such kind of equations are we have already learned that how to solve these equations, that is just by putting into the form, that is the equations of constant coefficients and right hand side not equal to 0 in this form, and we already know how to solve these equations. Now we move towards the last type of these equation, that is the reduction of the order, where we have for example this equation y double prime of x y prime and g of x y is equal to 0. Then we solve this equation by making this substitution and reduce its order. For example, if we put y is equal to u function of x and v function of x, then this will reduce to this form, x cube y double prime plus xy, and this is will be we can now this is an example of such equation which is multiplied by some function of x with the first term and some function of x with the second term. And if you want to reduce it, let y is equal to uv or is equal to xv, and then y prime, you can calculate the y prime and y double prime from this substitution. And if we make this substitution there, then this equation turns out to be this one, and or we just reduce it to this form, x for v double prime 2x cube minus plus 2x square v prime is equal to 0. So then such equation can be, you can see that is put into this form, and here we get the only first order derivative or the first derivative, and you know that integration of this will give us the natural log and these terms on the right hand side. And if we further solve and put back our substitutions, we get this final form of the solution. So and these are the references. So to give you the summary of what we have learned today, we have learned how to solve different types of equations where the coefficients are not constant. I given you the 5 types in this lecture, where in the first type the x was missing, and the second type y was missing. In the first type y was missing, and the second type x was missing. The third type the first derivative of missing, and then the Cauchy equations, and then a method of reducing the order of equation. And all these methods, one thing was common, that we made some substitutions, and after these substitutions equations were brought into the form which were readily soluble. So these equations are important because we have different physical situations which we can model with the help of these equations. In future lectures I will even give you more such equations and their methods to solve. With this, I thank you.